All right, thanks so much, Sydney. Hi, everyone. My name is Jacob Deva Racusin. I use he, him pronouns. I'm with New Frameworks, which is a design and build firm in Vermont. And I also work with Builders for Climate Action. I'm wearing that hat today to talk about the BEAM tool, Building Emissions Accounting for Materials. So just to give you a sense of the flow for the next hour, I'm going to start with some kind of overview around why looking at material carbon emissions is relevant. And then get into some of the details of the accounting practices and then some specifics around the BEAM tool in particular and how that can be used to help take some accountability and action over the carbon emissions of the building materials that we specify and design into our projects. I am really not good at looking at the chat while also presenting, so my intention is to leave plenty of time for some questions at the end. I'm happy to stay a little bit past the hour for those that are particularly enthusiastic. But if I say something that is unclear, if I didn't define something terribly accurately, or there's something that you're not quite understanding, please by all means just click yourself off mute, interrupt me, and ask for a clarification question. That's fine. But for any of the questions that are like, well, what about this scenario, or I have this other idea, that's awesome. Write them down, and we can go over this at the end because I may cover that over the course of the conversation. All right, well, let's just get right into it. Stand by here. There we go. So it should be no surprise to anyone at this point that we are no longer looking at the impacts of the climate crisis as a future case scenario. This is very much a lived condition for us. Those of us here in the AEC industry, specifically in the design community, our sector is responsible for about 40% of global emissions. So that's our stake in the game here. It's our opportunity. We have a huge amount of leverage in helping to dial down the emissions profile of our projects. Because as architects, we have a lot of control over what these buildings are and how they're developed. I want to highlight, there is so much we could talk about just on the operational side of things, and I'll talk about that a bit for sure in broader context. But I'm really going to be focusing primarily right now on embodied carbon in general, and specifically material carbon emissions. And if we're looking between building and infrastructure, concrete, steel, and aluminum alone are responsible for 13% of global emissions. So just highlighting those three materials within the context of how our buildings are produced, that is a huge volume of emissions that we've got agency in addressing through our design practices. So that's what we're going to really be honing in a little more specifically on for the course of this conversation. And just to kind of put operational efficiency in context for climate action, I come from an energy background, energy modeling, energy management background. And so for many years, it was all about energy efficiency and reducing energy intensity of our buildings as the primary mechanism for addressing climate change. And I want to start by saying, absolutely critical, still very true, and all of the efforts we do to draw down the energy loads of our buildings are fundamentally important towards hitting climate action goals for our industry. Unfortunately, they're insufficient alone. We need to do more than just make our buildings more efficient. Necessary but insufficient would be the way I would describe that. And just to give a little bit of context, so Builders for Climate Action, in addition to developing the BEAM tool, we do a lot of research on topics of material carbon emissions, and we've been involved in a whole series of benchmarking studies in various municipalities. So I know you're not all necessarily working in low-rise residential, but it presents for some really good simplified case studies. So we're going to just give some data points to quantify and scale the impacts of emissions a bit, just to, again, put the embodied carbon, the material carbon emissions in context of why this is important and how this can get woven into your practice here. So looking at an average two-story home, we see that every year it's releasing close to 3 tons of emissions a year. And over the course of time, those emissions on an annual basis continue to add as we dramatically reduce the increase the efficiency and reduce the operational loads. That has the effect in many cases of reducing the carbon emissions from the operation of this material. So we see that line being much lower. There's much less added to the atmosphere on an annual basis for a much more efficient building. But we don't necessarily know we certainly don't know what the real climate impact of that build is if we're only starting at operation and not looking at any of the upfront emissions that came from the materials construction practice to get that building into form in the first place. So whereas those previous graphs were showing those lines starting at a 0 mark, that's actually not accurate. They're starting with some carbon footprint entering into the life cycle, and that is the other part of this equation that we need to address in our carbon accounting. And so looking from some of the results of this benchmarking work we've done, just looking at existing buildings, this isn't hypothetical, but at benchmarking as-built buildings, the worst case scenario of some of those carbon intensive buildings radically dwarf what the operational profile is of a really low load building. And when you couple that with an inefficient build, we have blown our carbon budget radically. Middle of the sort of average upfront material emission profiles start us at about 50 tons. And then of course, there's an average incremental operational load into the future on top of that. And it's really not until we combine low load operational buildings, high performance buildings, with low embodied carbon construction practices that we can actually get towards real net zero construction and net zero buildings, meaning net zero carbon and decarbonizing the building industry. So until we really understand the material side of things, we don't actually know what the full carbon impact is of our projects and whether we're going to hit our decarbonization goals for our industry by the middle of the century. Looking at that another way, kind of the same data from a different data set, but the same sort of blending of the operational and the embodied emissions. When we're looking at those in various combinations of higher embodied carbon, lower operational, or vice versa, these sort of mixed conditions in the middle there, we see they're kind of hovering on either side of average. And it's really not until we're reducing our impact in both of those categories that we really actually get towards a true low carbon build. So that's really sort of the fundamental justification as to why we have to expand our field of accounting, our field of view, and recognize the impact that we're having from the material selections that we're making to really be able to hit the carbon goals and go beyond just addressing energy efficiency as the only mechanism for addressing the climate impact of our work. And so I'm a big fan of goal setting in projects and establishing really good goals and good metrics to be able to achieve those good outcomes. And I see in a lot of projects that I work on, particularly as a consultant, that this energy use intensity or the operational energy of a building is what's used as the primary goal for addressing climate impact. And again, absolutely necessary, super, super, super important. What we saw from these other graphs is you can't get a zero carbon building if you're not managing your energy loads really well. But it's just not enough to stop there and say, in addition to looking at the energy intensity, that energy really does need to be converted into carbon emissions. And that involves looking at the energy source emissions and what is providing that energy and the carbon impact of that energy. And as we're moving towards electrification, we're learning a lot more about how just looking at that on an annualized basis isn't enough, and we actually really need to look at the time of use of the emissions and the different emissions profiles that come from the peak loading on an electrical grid. So there's a whole lot there that needs to get unpacked. It's a little bit beyond what the scope of what we have time to talk about today, but as we're setting goals and setting priorities for our projects, if the goal is really around climate impact, not just setting energy targets, but setting carbon targets, not only within the energy side of the equation, and the operational side of the equation, but also adding these upfront carbon emissions as well to get a metric, say, of carbon use intensity, if you were to blend those together, or at least recognizing that both of those need to be held within the goals and the metrics of success that are being developed for a given project. Because ultimately, what we are learning, what we know from the IECC is that we need to get to zero carbon industry by the middle of the century. We have to address it across the life cycle of the building. And we're simply not going to get to zero unless we also hold and value the role of carbon storage within buildings as well. Because we are still going to need glass and cement and concrete and other emission-related materials to be incorporated into our projects. So we have to find a way of balancing out that equation to actually get to a 0 point. And we'll talk a little bit about carbon storage as well. So that's the bigger picture accounting that I want to hold for us as we're looking at some of a more specific dive on the material carbon emission side of this equation here. I want to give a little bit of sort of definitions and some terminology and explain some of the letter jumbles that you'll see up on the screen. So when we're talking about when I use carbon and carbon emissions, that's really a shorthand for carbon dioxide equivalents. And those are the units that we're measuring when we're talking about the global warming potential, or the contribution to climate change that comes from the emissions of our materials and our building operations. And so that little E that you see at the end of the CO2, that equivalent, means that it's not just looking at carbon dioxide, but all of the blending of all the different greenhouse gases and equating those to converting them to their equivalent value of impact as per a molecule of carbon dioxide. So an example of that would be methane. Methane is definitely released through the production of materials, as well as say natural gas that may be used on site. So methane over a 100-year period of time has about 34 times the impact of the molecule of carbon dioxide. It's actually closer to 80 within a 20-year period of time. Nitrous oxide, significantly higher. We get into R410A and some of the refrigerants, and those can be thousands of times the impact. And so their value in the case of methane would be 34 kilograms of CO2. So whenever you see that little E, it means we're talking about all the greenhouse gases that are contributing to climate impact. When I talk about carbon from the standpoint of carbon storage in like a bio-based material, I'm literally talking about the element carbon that's in that material. And then when you see a carbon dioxide equivalent value from that, we've done the math to understand how much carbon dioxide has been photosynthesized out of the atmosphere that is then embodied into that material. So I'll try to be intentional around my language around carbon. Sometimes I'm literally talking about carbon, sometimes it's carbon dioxide, sometimes in the context of carbon emissions, we're looking at CO2e for all of the greenhouse gases. So again, looking at this need to get to zero emissions in a combination of both the operational and the material side of things, there are lots of really good tools and rating systems and structures on the operational side. So I'm not going to talk about those. There's plenty of those out there and really good resources for that. We developed Beam to help address the material side of that. And there's other really good tools out there as well. I may draw up some references to those too, but that was really the intention, is to fill a hole in the tool sets to be able to quantify and help manage the material emissions side of things. So again, why this felt really important, to give a sense of scale as to why this felt really important to address. We looked at that from a global perspective at the beginning of the talk here. Again, we've done a lot of benchmarking of many, many homes, larger buildings as well, but in the context of homes, we've sort of recognized that an average emission profile across our benchmarking studies of about 200 kilos per meter squared of building area. You multiply that out by new low-rise residential construction, and this was from 2017 numbers, and we get 50 million tons of annual emissions just from that one sector of the built environment. That's not even looking at more structurally intensive mid and high-rise structures. That is equal to or greater than the entire sort of national emissions of some many major developed countries. So this is a really big deal. There's a lot of carbon, a lot of emissions that we have the opportunity to help manage and address by first daylighting the accounting and the scale of those emissions, and then using a tool and a analysis strategy and a design process to help turn the dial on what materials we're selecting and how we can reduce that impact. As I mentioned, there's a bunch of other really good tools out there. One thing I really love about being in the embodied carbon space is that it's a very open source, collaborative, kind of all-in sort of community of practitioners and tool providers. And so most of the tools that we had been working with when we were starting to do a lot of our work were really organized by and designed for practitioners of larger structures, which is wonderful. That's obviously a very important place to intervene, but there was very, very little available to smaller firms working on smaller buildings, or even for firms. I've done plenty of work on mid-sized construction. A lot of the consulting work I do is in the sort of 10 to 50,000 square foot building size. but not necessarily with in-house life cycle assessment experts, maybe not always working with BIM modeling tools that a lot of the other tool sets require to really be able to work, organize into a workflow, and particularly seeing that 95% of the buildings that are responsible for half of the emissions of our building sector in the country really didn't have easy access to those tools. We saw a need for a tool that was much simpler, more flyweight, easier to integrate both earlier into the design process and throughout the design process for smaller projects and smaller firms with smaller budgets. So that was the initial impetus of developing BEAM. We've since used it for a lot of research. I mentioned I use it as well for larger projects, and through some of the research, it's been really illuminating as we've benchmarked existing housing stock in various communities to see what a broad range there is of the emissions profile, the material emissions profile of these different buildings. Nearly or over a 4x difference from the lowest to the highest results, just looking at about 500 homes in the Toronto region. So this gives a pretty good sense of not only what the span is, but how much opportunity there is to bend down the curve, some of those highest results to be meeting what's practical to build and has been built on the lower end of that spectrum. What's also been really exciting to look at as we've been sort of digging into the details of a lot of these case studies is that it doesn't necessarily require these big sweeping radical moves that have to be, fundamentally disrupt your base specifications or your design approach. A lot of in this sort of example here, we're showing you can get 75% reduction by a whole series of essentially simple substitutions of common materials. Taking a first bite by reducing the carbon intensity by adjusting the concrete mix formulation, another really big bite by replacing XPS and fiberglass and mineral wool to cellulose and bio-based insulation, so on and so forth, with changing out the continuous insulation, changing out the exterior cladding, and then just using best in category flooring and drywall selections. And so none of these are radical, expensive, hard to implement solutions, but can result in, again, a really, really significant reduction of those upfront carbon emissions. So just to help bring into the conversation early that this can be done incrementally, it can be done in a series of steps, and you can make really large improvements without having to push immediately outside of a comfort zone in adjusting your preferred design practices and material selections. So that was a really big goal for BEAM, was to be able to use BEAM and have a tool set developed that could be used for comparative analysis, particularly within the material profile or material part of the building's life cycle. So you can sort of see a layout of the tool. It's in a sort of spreadsheet format. And we have chosen to list out all the materials that are available for selection and list what their emission profile is, and be able to do direct side-by-side material comparison without even having to run reports or complete a full tool set or tool process. Just right out the gate, be able to start comparing and begin the analysis process. And I'll give some examples of how you can run everything from material comparison to assembly comparisons to working through some design development approaches as a design aid tool, as well as looking at whole buildings and whole material bill comparisons. Another thing that was really important for us in BEAM, I said earlier that it's really important to look at the realm of carbon storing materials as part of the solution set to get to zero carbon buildings. So it was we, as the developers of the tool, come from a background of really leaning into bio-based materials as part of our material profile. And so we really made sure to go out of our way to include some of the quote unquote alternative or the less common, more innovative materials that are market available and market ready and sort of proven, but are frequently missed in a lot of the more sort of conventional and basic material sets. So if you're looking for cork and wood fiberboard and straw and some material ag residue, earthen forms of construction, we've really gone out of our way to prioritize including those in the tool set because they really are valuable solutions for our decarbonization strategies. So I want to talk a little bit about life cycle here, both in the imperative of why looking at material emissions is important, as well as to explain what is included within the scope, the boundaries of the BEAM tool. So when we're really looking at the carbon emission profile of a building, we're looking at whole building life cycle assessment. That life cycle begins with the extraction of materials, raw materials out of the ground. That's mining for ore, or extracting fossil fuels from the ground, or cutting down a tree. That would be that A1 raw material supply. And then it goes through transportation process to get to a manufacturing facility in which those raw materials are manufactured into products. That boundary, A1 to A3 in LCA parlance, is the cradle to gate, or meaning factory gate boundary. And that's what we call material carbon emissions, because we're really just comparing different material and different products as they're sort of leaving the manufacturing facility. There are additional steps prior to occupation, transporting those materials to the site, and then of course the construction process itself. And then we get into the use phase. Operations and the heating and cooling and lighting and powering of our buildings is by far the biggest emission category within the use phase. But there are also maintenance and repair issues that come up, and additional materials that are consumed, especially depending on the nature of the building and the longevity of the material. So that's another category of material consumption and emissions that happens. And then, of course, is the end of life, and how those materials, both the deconstruction demolition process and the transportation of those materials off-site into waste processing disposal facilities, and then the emissions that are released either in the processing or the actual chemical release from the materials, or the decomposition of some of the bio-based materials. All of those add to the end of life scenario. And so in the BEAM tool, we are very explicitly just looking at the material carbon emissions. This is not whole life cycle analysis. We are not looking at the full cradle to grave sort of span of the material or the building's lifespan. We're just looking at the material carbon emissions. And we do that for a few reasons. There's by no reason to say that's better. In fact, I would advocate for those that are really trying to understand and manage their carbon profile, it's really appropriate to look explicitly at the materials profile as well as at the whole life cycle. And looking at both those boundaries is quite relevant if you've got the bandwidth and the interest and the capacity for that. We chose to really focus on the material carbon emissions for a few reasons. One, we believe that the materials that are emitted today and prior to the occupancy of the building are some of the most important emissions to manage. And for two reasons. One, if we're trying to hit near-term emission reduction goals, then we need to reduce the emissions that are being produced today. While I'm a diehard advocate of low load and low energy buildings and electrified and renewably powered buildings, those emissions are released annually, incrementally over an 80, 100, 150-year lifespan of a building. We don't really have that period of time to realize our reductions. We need to be realizing those reductions immediately. And so the phase of time in which those emissions are released are prior to occupancy of the buildings that we are designing today. So it's very important to be looking at those emissions. Those are also the emissions that persist for the longest period of time over the lifespan of the building. And so the fact that they're released early and persist long also heightens the value of really addressing that plume of emissions. Another reason we're really focusing on that is because the majority of the emissions, this very much depends on the material and on the building type, but in our experience, we found that the majority of the emissions in our building's lifespan are really released during that, in that material development process, in that cradle to gate. So that felt relevant to really focus on that larger package or that larger sort of plume of emissions, as well as that's the best quality data that we had, the least speculative and the sort of best defined data and most comparable data comes from the EPD sourcing, which is the environmental product declarations, which is the data set that we're using for these various products. And that's the highest quality data set. So for us, while we're trying to create an easy to use, simple to understand, quick to deploy tool, really focusing in on that boundary made the most sense, knowing that there are also really high quality life cycle assessment tools available to use as well for looking at that full life cycle of the building. Beam is a free tool that right now resides as a Google Sheet application. So we basically tricked out and made very pretty a Google Sheet. We are excited to migrate this to a standalone application in the not too distant future, but this was the most inexpensive and fastest way for us to be able to get this tool out into use in the world. We have many hundreds. I think we may be in the thousands now of registered users. As a free download you can get from that URL. Or do a quick Google search for Beam tool and you will find it. I encourage you all to download it and start playing with it. And if you find it of value, please consider contributing to the use of the tool, because this is a community-funded project to keep improving upon it. And I'll talk about a new release that is coming out with some improvements at the end of the show here. But just to give you a really quick walkthrough of the tool, so you have a general sense of what it feels like and what it looks like. Again, it's a spreadsheet format. So those of you that live, or at least have some acumen with spreadsheets, this will all look very familiar. We really designed this to be a very simplified, low input tool. So any of you that have done like sort of box model energy models, where you're just putting in some general assembly dimensions, that's a very similar analog here, where we're asking for some basic inputs of some of the major parts of the building. For example, your exterior wall area, to include that. There's some descriptions and instructions of what to include and what not to include, as well as some organization around how those inputs are used throughout the tool. So if you're ever unsure of a value, there's a lot of information on the logic of the tool and how those inputs are being used throughout the tool. And then there's a whole series of different tabs you can see at the bottom here that capture each of those different assemblies in the building and gets into much greater detail. And so within any one of those assembly tabs, in this case looking at exterior walls, you'll see there may be some additional inputs. In this case, you need to input the R value of your installation to be able to get some readings back. That's the input basis that you are comparing your different installations against. And then when you say, okay, I'm going to select wool, goose fill wool is my installation of choice, you simply click the checkbox. This highlights the selection so that you know that's been selected, and it adds it to a subtotal at the top of the page, as well as to the summary pages at the end of the tool, which we'll get to in a moment. So that's as simple as clicking and unclicking a box allows you to select and deselect materials, which also helps as a design aid. You don't have to run through the entire iteration of the tool and get results and then repeat. You can make a bunch of modifications and selections in real time as you're navigating through the tool. And again, as I mentioned before, all of the comparative analysis of the different materials for a given R value are revealed just in looking through the different entries of the different materials, which can be really useful in terms of just getting a sense of scale of impact of choosing material selection A versus material selection B. There are 12 assembly sheets total that you would navigate through to select the materials that you would need for any one of those assemblies. And there are some additional input factors that are specific to the different parts of the assembly. We talked about R value. That would also include framing spacing for stud or metal framing, your wall thickness, for example, for your concrete wall, so on and so forth. So some of those additional inputs will show up as required throughout those assembly pages. One of the next, once all of those have been filled out, or as many as you so choose, you do not have to fill all of them out. And we'll talk about that for some different approaches of how you can conduct analysis here. You will see a listing of everything that you've selected, as well as some color coding of the intensity of the emissions for those various materials. And so the orange color palette are indicating what the emissions are, and the green palette are indicating what some of the carbon storage is. And I'll take a moment here and show, you may have noticed earlier in the pages that there's actually 3 different readings that show up here. The carbon emissions are the gross emissions, however much or however, whatever tonnage of or weight of the carbon dioxide equivalent emissions have been released into the atmosphere. That is what's captured in carbon emissions. The amount of biogenic carbon that has been stored that we deem is meritorious of carbon storage, and we can talk about. So, for example, we do not account for virgin wood as a carbon storing material because of the complexity and lack of transparency in wood supply chains. However, we do include wood and agricultural residues and bio-based recycled materials like post-consumer installations, paper installations like cellulose, as qualifying for carbon storage. And so we break apart that value separately so that that's transparent, and then show what the net is, which is the total emissions minus the storage. When we total things up, we put a 10% duration value on the storage as a conservative measure, knowing that 100% of the carbon that's in that material may not directly equate to carbon dioxide removed from the atmosphere. So we were a bit conservative there in that math, but we make that math very explicit so that if you, for whatever reason, choose to not include the carbon storage in part of your analysis, you have the gross emissions values there. But here on the review page, you can see all the materials and what the line item emissions and storage values for those materials are, as well as what the subtotals are, and a quick visual scale of intensity. I find this to be an incredibly useful page for quality control in being able to compare this list back against your bill of materials and make sure you haven't double counted anything or left anything out. And then there's a results page, and we'll walk through the different components of the results page formatted to an 8.5 by 11 format, so it can be printed out or burned into a PDF to be able to share with the rest of your team, communicate the results to a broader audience. So part of what we have done in tricking out the Google Sheet, we've done some custom scripting. And when you first load up Beam, you'll be taken through a series of menus to accept and approve custom scripting. We promise we have not embedded any malware or harmful coding into this tool, we promise. But we have a custom menu here that allows you to save your projects and reload them and compare different versions of those projects. As well as toggling between metric and imperial. This tool was developed by a Canadian group, and so you'll see there's a lot of metric information here. Don't panic. You can both convert from metric to imperial, as well as just toggle the units. If you entered everything as an imperial value but didn't realize that the metric was what was selected, you can just change the unit description as well. So a bunch of different customized features that make as a professional to be able to load multiple different projects and multiple different versions of a project to do comparisons between different alternates, or a baseline versus an improved comparison. Looking at the reports page with a little more detail, see that we have kind of a few different sections. The first section there, which is not highlighted, is just some of the same basic building information that you have entered in the beginning: the name, the location of the project, who some of the project partners are, some square footage information, so on and so forth. We have a breakdown of the material carbon emissions by each of those sections of those assembly tabs, so you can see what how the disbursement of carbon emissions for your project breaks down by those assemblies. In this case, we can see that the footings and slabs and foundation walls are where a lion's share of the emissions are, as well as the garage. And so in this tool, we have included a section for adding a garage or another outbuilding or porches, if you will, or some other additional structure that's outside of the primary building, that you can add that into the tool as well. The square footage of which is not included. So if you're looking at, and I'll get to this in a minute, you can do an analysis based on carbon intensity, which is on a sort of per conditioned square foot basis. In this case, there's a lot of emissions from the garage, but no one is living in this garage, and so that gets burdened onto the project as part of the total emissions, but there's not a credit leverage for additional habitable space. So just some additional explanation of what can be incorporated into the analysis in the tool. But so we can look at this on a per assembly basis, and then we can also look at some of these totals. So we can look at what the net emissions are for the projects, as well as this, again, material carbon intensity. So that's on a per square meter or per square foot basis. So in creating a tool set that can work for both metric and imperial based markets, we've got those the intensity broken into both metric and imperial reporting, both for the total area as well as the conditioned area. And you'll see if you were to go back to that initial project entry form, you can enter in both the total area, which would include unconditioned area for the building, as well as just the conditioned area, depending on how you're choosing to run your analysis. We also have a scale based on our benchmarking of how good or bad of a number is this. We recognize that we are still very early in the process of getting a good sense of smell of what constitutes a good or a bad value for material carbon emissions. And so we've provided some scalar inputs there. I will note, and I'll get more into this at the very end here, we have done a lot of work to revamp and improve the legibility and some of the additional information in this reporting, particularly in this view here, in the next version of the tool, which is going to be coming out by the end of this quarter. So you can look for that as you continue to download and work with the tools and enhance reporting. We also break out some of the highest carbon material applications. So if you're really trying to use this as an iterative process, as a design tool, and not just as a reporting tool, this will very quickly lay out, here's where all the carbon is, not just on a per assembly basis, but on a per material basis. And so in this case, we're seeing that the walls and the slabs are really jumping out. The garage is a full category, so the garage is actually held as an entire, those at-bones be held as an entire entry, so on and so forth. And then we'll also see, it's actually not highlighted, but the best material storing applications are also listed as well. So just to kind of move us along here, just to give some examples from an analysis basis of how you might use the tools and different types of analysis that you can use with the BEAM tool. One is just looking at a simple material swap. So here we've got two basic, very simple wall assemblies listed, and you can see within the section of exterior walls, we've got some framing, some sheathing, some cavity insulation, and some continuous insulation listed. And we wanted to do a sensitivity analysis of how big of a deal would it be if we were to swap out an average mineral batt product for an average cellulose, dense packed cellulose product. And you can see both on the line item as well as on the subtotal for the assembly, wow, that makes a really big difference. Okay, clearly there's a significant value from carbon reduction in making that simple material swap. You don't have to input anything more than that. It'd be quite reasonable to just put in 100 square feet or 100 square meters for that assembly and just run this analysis, and you can just stop right there and consider that a successful use of the tool. You can also use it to compare different assemblies to each other. And this would be, okay, well, maybe we'll do this as a stud wall construction, or maybe as insulated concrete form, or maybe as a structurally insulated panel. What's the diversity of carbon impact for a few of these different assembly types? That gives another way of using the tool, zooming out, not just for a material swap within an assembly, but comparing different assemblies to each other. There's a few different ways you could organize that, and saving some different types or some different alternates of the project to be able to recall those at any moment. So that's yet another sort of zooming out a level of analysis. You can also expand that, not just to the core services of structure, insulation, and enclosure, but also to add some finishes to that. You may choose different finishes based on your assembly type. So this is just moving outside of only the exterior wall section, but including the claddings. So now we're zooming out a bit broader in the boundaries of our material analysis. And then, of course, you can zoom all the way out and look at a whole bill of materials for a project. And in this case, we're looking at, again, a pretty significant reduction, 75% reduction between these two projects. And the analysis work would then be to look on a line item basis and really see what some of those changes are to lead to that cumulative reduction of emissions across the whole building. So just giving you a few different scales of an analysis boundary that you can use the tool for, depending on what your needs are in the design process. I'm excited to share that the tool launched initially geez, I think about a year and a half ago, if my memory serves. So it's been out in the world a little over a year, maybe not quite a year and a half. We've seen a whole lot of take from it, and gotten a lot of really good feedback. So we have a series of improvements that our team is actively in the process of implementing into a revised version. A whole bunch of new EPDs and updates to again, EPDs are the environmental product declarations, which is the data backend to the tool. We've improved the scripting to make the saving and loading a bit faster, and make it easier to do some of that comparison. As I mentioned, you can save different versions of the tool. We've improved the ability to compare across different designs, the ability to add your own EPD. If there's a product that you found some data for that you don't currently see in the tool, you have an ability to import that yourself. As well as some pop-up notes and some the ability to make some notes and sketches for your own organization within the tool. We have expanded the menu for custom concrete EPDs because those mixed formulations can be very, very specific, and there are now tools out there to do custom digital EPDs for concrete. So we've brought some of that functionality into the tool. New barriers category for some of the membranes and control layers that were previously not included in the tool, as well as some enhanced instructions and information around tool usage. So those are all things you can look for in the months ahead. I would say you should wait for that to come out. Go ahead, download the tool, start working with it now, but just to encourage that there'll be more good things to come. So again, we encourage you to give it a spin. I find it's a really quick and easy tool to learn. The learning curve is pretty gentle, I would say, particularly if you have some experience working with spreadsheet tools. Again, we are a really small, passionate nonprofit that's been producing this tool. So if you do find it as a value, we greatly appreciate your financial support to allow some of these improvements and ongoing maintenance of the tool to keep it going. And I want to draw your attention to an online course. We run a series of training courses a few times a year. If you're really interested and want to climb up that learning curve a little bit faster, get into the weeds a bit more, and improve the accuracy and efficiency of your analysis around the material emissions of your buildings, we have an upcoming training, an online training that will be the synchronous version of which will be starting in September 19th. We have a pre-recorded session that just gives a lot of the sort of baseline terminology and definitions that is available right now. So you can go over to the buildersforclimateaction.org website and find a link to that training course, and we'd love to have you join us later on this month. Okay, I know there's a bit of a whirlwind tour, but I wanted to make sure I left some room for conversation and discussion. So I will pause there. Maybe I'll stay on that page in case you're all interested. And I see there's some items in the chat here. I'll bring that up and invite you to come off mic, come off video, and we can chat. Let's see, I'm just going to go through what's already in the chat here. Is there a BIM interface in development, open source for the BIM analysis tool, and or are there efforts to use AI for optimizing outcomes, improved practices forecasting? I love it. AI is showing up everywhere. So no, we do not have a BIM interface, and that's actually partially by design. And I'll speak to a couple of reasons for that. One being that, well, a few reasons. So one, there are some really, really great BIM integrated LCA or lifecycle assessment tools that are available, some of which are free, that I'd highly recommend, and that I use myself. And so that space is sort of well supported right now. My own experience as a carbon analysis sustainability consultant is that it is very frequent that a good, useful BIM model has not been produced in time to conduct early phase analysis. And so, for example, for those of you that have come from an energy background, this may sound familiar, you have the largest amount of influence for the least amount of financial and logistical burden to change the trajectory of a project earlier on in schematic design, first half of SD, where you can still play with the massing or really inform some of the major decisions around the structural grid. often a BIM tool in a sort of conventional design workflow isn't going to be developed until after those decisions have been made. And at that point, you may have lost some of your most impactful timing to do good analysis and inform the trajectory of the design. And so I have used Beam explicitly for doing some of this sort of really flyweight, quick, sort of high-level box modeling or some direct material comparison early on before a BIM model has been fully developed. And then by the time we move into design development and the model has been populated, at that point, we may even switch to a different analysis tool. And I will often use a lifecycle assessment BIM-based tool alongside Beam to do some quicker studies or some quick material analysis so throughout the design development and even the construction documentation phase. And so I'm not expecting that we will move to a BIM platform anytime soon. The question about AI is a great one. I will acknowledge that I have not been keeping a pace of the developments and opportunities that exist within the world of AI. However, I know this is something that is very much on our radar. And as we continue to explore migrating off of the Google Sheet platform into a dedicated application for the tool, I do expect that this will be part of the development process to see how we can leverage AI to help make the analysis experience that much easier. How are the carbon storage numbers calculated? That's a great question. So the methodology we use for carbon storage is essentially reverse engineering, if you will, from the carbon content of a given product. So I'm going to use cellulose insulation as an example, as a very sort of common carbon-based product that we give a carbon storage value for. So within the environmental product declaration sheet for a given cellulose product, it will tell us what percentage of that product is actually bio-based. And so we'll take the mass of the total cellulose that's included. Then we will take the percentage of that is a bio-based product. We then use a database, the Phyllis database is the most common one we use, although there's others that we may source as well, to understand for the biomaterial, in the case of cellulose, that would be wood in the former recycled paper. For that material, what percentage of that biomass is carbon? In the case of wood, it's roughly 50%. And so now we've sort of measured out or metered down the total weight to the amount of carbon that is present in that given product. We then convert that carbon by the ratio, the molar weight ratio of carbon dioxide to carbon to calculate how much carbon dioxide was photosynthesized by that tree to embed that mass of carbon into the tree. Then we, as I mentioned earlier, we will derate that by a 10% value to account for some additional inefficiencies or waste in the system that may be present that isn't fully transparent in that accounting. So again, trying to take something of a conservative value in that carbon storage accounting. And that gets us back to a CO2e value that shows up as a negative emission. So since that carbon has been effectively stored within the material for the duration of the life cycle of that building, we are giving it a negative emission value. A few more notes around that, because it's something of a controversial, developing, maybe potentially confusing topic. A few more sort of things I'll offer around that, because we recognize we're one of the few tool sets that really gives a good granular unpacking of on a line item basis of what that carbon storage is. I mentioned earlier that we don't give credit to virgin timber materials. It is actually something we're looking at. I'm unclear, but it's certainly under consideration and may be included in the next version of being able to identify what that value would be, but not necessarily including it in the totals. The reason that we're not including virgin timber is because it is a very, very complex accounting to say whether or not there is a net benefit to the atmosphere for having cut down that tree. And it can be species specific, application specific. It's certainly bioregionally specific to the forest, and often involves some degree of speculation on, well, what's the counterfactual scenario for that tree? Would it stay living in the forest and continue to photosynthesize, or would it actually have been cut down anyways for development? Is it part of a forest management plan? Can you be sure that the the wood that you've included in your project is actually coming from that specific forest, or is mixed with a bunch of, say, uncertified or unvalidated wood if it's not all coming from a sustainable supply chain, so on and so forth. There's a lot of questions, and forest ecologies are very complex. So for that reason, we're again taking a pretty conservative approach in not out of the gate just giving credit to those virgin materials. However, wood residues, agricultural residues like straw or hemp, and certainly post-recycled content materials like the cellulose I referenced, we can say that were it not for being incorporated into a product, all signs would point towards the carbon in that material would be re-aerosolized into the atmosphere within a relatively short period of time, either through burning or decomposition or landfilling, what have you. And so we feel good about giving a storage credit for those materials being incorporated into the building. We also feel good about being able to provide a negative value within that upfront part of the building's life cycle. Now, we know in sort of conventional life cycle assessments, that same negative emission that's credited at the beginning of lifespan would be seen as an actual emission, would be no longer storage, but an emission at the end of the life cycle, with the expectation that all of that carbon would end up back into the atmosphere. That's not necessarily what would happen, but that is certainly one outcome. And it shows that by the end of that project's lifespan, that may be part of what would need to be accounted for. We could talk for a long time about dynamic versus static life cycle assessment, and meanwhile what that 100 to 150 year impact on the atmosphere is for having avoided those emissions for that period of time, and how much of a benefit to the atmosphere that might be. That gets into a bit more into the weeds and nerdiness than we'll be able to cover in the last 5 minutes or so here. But that is part of the consideration, giving a negative value in that upfront boundary of the tool. And again, for those of us that are really trying to look at full life cycle assessment, that's where also using a life cycle assessment tool would be important. It's also, I'm going to call out the difference between storage and sequestration. I know different folks will use different definitions for that terminology, and will sometimes use them in exchange with each other. I tend to consider sequestration something that's over a longer period of time, like, for example, injecting carbon dioxide into concrete, something that's a much longer carbon cycle. I would use sequestration for that duration of carbon management. Storage, by definition, to me, implies something that's a little more temporal and could be reversible. And that's a very real consideration with bio-based materials. We can get into a whole other conversation around the accounting of short cycle versus long cycle carbon, and I recognize this opens a very large can of worms. We're just sort of dipping our toes into that, but we do feel it's a really important part of the accounting and equation of how we are managing for our near-term immediate carbon reduction goals, and recognizing that the carbon that is in those materials is carbon that was in the atmosphere and has actively been photosynthesized and drawn out of the atmosphere and stored into a material. And that does deserve and requires accounting for in this early phase. And then it's our responsibility as analysts and strategists as to how we manage that accounting, what's a very complex cycling of time over a building and a product's lifespan. Glad to hear I addressed someone's considerations around mass timber. Again, we could speak for a very long time about the biogenic carbon conversation. Let's see, I think I see one more question in the chat here. Is there information provided in BEAM on baselines for different building types and scales? What's poor, good, excellent carbon value for each building type? Great question. I would say, yeah, that scale you saw there is informed by the benchmarking work that we have done, primarily for low-rise construction. We don't have it broken out for multiple different building types. It's a little bit beyond the scale and the capacity of our tool set to include that density of sort of baseline information. I'm going to point you towards the Carbon Leadership Forum as a fabulous source for benchmarking and baseline information. They have an initial benchmarking tool that was and a report that was released years ago, and they are in the process now. It may have been completed. I know they're certainly in the process of updating all of that, and I would definitely encourage you to use that as a good tool for being able to compare different building types and the baseline expectations for those building types. Because we have done so much of that research in-house for low-rise construction, we're able to embed that into the tool really effectively, but I wouldn't necessarily use that for mid or high-rise construction as an appropriate guide for baseline. Let's see if there's any, will a recording be available? I'm going to defer to Sydney to inform that, but I'm expecting so. And yeah, the baseline number. So I guess the other thing I'll append to that would be, I would encourage you, yes, there will be a recording. So keep your eyes and ears out for that. I will also distribute, I'll send to Sydney the PowerPoint, sorry, the PDF version of this, so you can have the PDF version of the slide deck as well for your reference. I'm also very much going to encourage you to go to buildersforclimateaction.com and check out some of the research that we've done. We've done some really, really good, well-visualized, easy to digest benchmarking and baseline analysis of the research work we've done, and there's a lot of really good information within that I would encourage you all to check out for a little more sort of detail beyond just the sort of static number scale. So that I'd say between buildersforclimateaction.org and the Carbon Leadership Forum, those are your best resources for more comprehensive baseline numbers. But again, that scale that you see in the results tab is informed by the research that we've done in the low-rise sector. And one just came in here. See, I'm happy to hang on a few minutes past the hour, but for those of you that are with me for the next couple of minutes here, are there feedback loops for as-built performance verification metrics? Promising applied practices identification. I'm going to see if I can interpret that question accurately. I guess when I hear are there feedback loops for as-built performance verification, maybe actually, Craig, I'm going to invite you to, if you're so willing to unmute, and maybe when I hear that question, I'm thinking like, how could that be used within a design tool process, or how would that feedback loop be for improving practice? Or are you more asking about how you would use benchmarking information from as-built conditions to inform your design practice? I mean, can you help explain that question a little bit further?
Yeah, so this is Craig. Can you hear me?
Yeah, I can. Thanks for chiming in.
Okay, great. Yeah. So there are a number of platforms that allow sort of an open source input for end users to bring back for the benefit of a community user group some promising practices with regard to practical application of this, and then feedback loops from how things are actually working in the real world. As, an outgrowth of the hypothetical to how it actually is performing. So that was the kind of bridging that gap from we are intending aspirational to do the best we can, but how are the feedback loops reinforcing our trajectory?
I love it. That's great. I will answer that kind of on two levels. In terms of being able to literally import a data set of or an input list from an as-built condition into Beam to sort of merge that directly into the tool itself. If that has initially been established within Beam, I believe that is doable, that you can share projects across users. I've not actually done that myself, and I don't want to speak too far out of turn, but my understanding is that can be done. And so if that as-built condition already exists within the tool, then that can be shared. You mentioned community practitioners, which leads me to believe that, hey, here's a condition that you can hold up against your own projects or do direct comparison against within the tool. I would say I would want to double back with their developer team and ensure that I'm not speaking out of turn that that's feasible, but that's my understanding. Zooming out a bit more broadly, I'd say the closing of that feedback loop, in my experience, is very much from the analyst and the human that cares enough to look at something that's been done and chooses to act off of that information to inform best practices as a design tool. And I'm going to sort of point back to the sort of what's incorporated into the structure of the tool, of being able, it was very much our intention to use it as an active design tool and not just a reporting and verification tool. And so the reason that we set up the format such that you could see the entire profile of materials incorporated within the tool and all of the emission and storage values for each of those materials without even having to select anything was very much to close that feedback loop that you mentioned. And so an example that I could give of that, even if you weren't taking an as-built set of inputs and bringing it into Beam, if you had just like a basic assembly profile and a total of, say, hey, this is what our last steel stud mineral or you know, closed cell spray foam infill with XPS foam wrap, wood fire or sort of cement fiberboard cladding, and you know, sort of standard gypsum wallboard interior finish wall assembly. This is sort of what we've done in the past, and here's a value for that. You could, within Beam, at a glance, just see what the improvement potential would be across those material profiles, let alone be able to then just select different material options and get some subtotals and do some of that assembly analysis. And so the way that I have used Beam, even actually specifically with BIM-based projects that are using lifecycle assessment tools, has been to use BIM as an iterative design tool based off of prior assemblies that, say, the construction manager has preferred, or that the design team has used in previous buildings, or that the campus has other buildings built as their sort of standard architectural approach for other buildings on their campus. That closing the feedback loop I find to be incredibly effective with the tool, where you get that immediate information. And I have done, you know, many dozens of meetings of screen sharing Beam with the project team and saying, okay, well, last time we used this installation or this assembly basis, let's just look at the screen, and you can just really quickly see the span of improvement potentials across any of these material categories. And that can just be done visually in a walkthrough prior to even needing to conduct a full analysis. And of course, you can then run as much analysis as you would like. But I guess that's how I would answer that in a slightly more macro form, and why the tool was developed the way that it was to enable design action and not simply reporting and verification. Let's see, 403, if there's another really burning question, I'm certainly happy to entertain it if you want to click off mute. If not hearing any voices interrupting me here, I'll just thank you for your time. I really appreciate you giving up an hour of your day to learn about a nerdy carbon accounting tool, and really hope that you download the tool and use it. And please join us later this month for the online training, and be in touch with the folks at buildersforclimateaction.org if you have any other questions or need for information, or feel compelled to donate to the further development of the tool. Thank you for your time.
Thank you.
Where to download the tool? Craig, go to buildersforclimateaction.org. Thanks so much, everybody. Enjoy the rest of your day.